Hi, my name is Victor Ciupec from VU Amsterdam. I'm presenting an experimental study aimed at investigating the performance and hyperparameter impact of using domain-specific datasets for training knowledge graph embedding models. The results obtained in this paper are compared against ones in anterior studies. Knowledge graphs form the backbone of a wide range of modern applications: search, question answering, social network analysis, drug discovery. They often are represented as sets of triplets in the form of subject, predicate, object, indicating that the entities subject and object are nodes in the graph and that there is an edge, a relation, in between them, which is then labeled with predicate. Knowledge graphs consist of real-world observations, therefore are not complete. One of the most commonly researched problems in knowledge graphs is link prediction. For instance, can new triplets be generated in the knowledge graph? There are several approaches to this problem: rule-based, knowledge graph embeddings, and hybrid. The KGE models learn embeddings in a low-dimensional vector space and use a scoring function to rank the triplets so that the true triplets have a high score and the false ones a low one. Majority of the KGE models were compared in the literature using generic benchmark datasets such as Freebase and WordNet. For the research, do KGE models perform better when trained on domain-specific datasets? And what are the hyperparameters with the most impact on the performance in this case? Our study is performed on two semantic web datasets: AFB, which records the research activity at an institute, and MUTAG, which represents the structure of chemical organic compounds for mutagenesis. Both are smaller than FB15K and WNRR. Both datasets have ontological structure and redundancy in expressing facts through triples. Both datasets split into 60% training, 20% validation, and 20% test. This study compares 5 of the most popular KGE models. These KGE model architectures differ mainly in their scoring function. Alongside the model architecture, we combine a variety of hyperparameter configurations to evaluate the model with each combination. The most important ones are training type and loss functions. The KGE models have been trained using 3 main different types, which differ mainly in the way negative samples are generated and used to calculate the scoring functions: 1 versus all, negative sampling, and K versus all. Transy is limited to negative sampling due to its architecture. Models that were either trained with cross-entropy or binary cross-entropy, except for Transy that was trained with the all loss functions. Other hyperparameters that form part of the study are embedding size, batch size, and learning rate, etc. During the validation and test phases, the models were evaluated using an entity ranking protocol, which uses metrics like filtered mean reciprocal rank and filtered hit at 10. They both work by assessing the average rank of test valid triplets amongst the scoring of the triplets obtained by mutating either one of the entities. MRR uses the mean reciprocal rank, whereas hit at 10 only counts correct predictions in the top 10. This table shows the best performance on the test data split. I include in the comparison with the results obtained in the Ruffinelli 2020 study with identical experimental setup on Freebase and WordNet. Across the board, the models performed the best on AFB, however the MUTAG also performed better than FB and WNRR, mainly on Dismalt. In our study, Dismalt had the best performance on test data, whereas Resco and Complex were performing better in previous studies. Dismalt performed best on AFB test data split, and Resco and Complex performed best on FB15K237 and WNRR respectively. This box plot shows the distribution of filtered MRR across the quasi-random, from the SOBO phase, hyperparameter configuration space. For each of the models there were about 200 configurations, except for Transy, which had 60. A couple of the observations we have received is that the median conv configuration is the best amongst the tested models, whereas Transy is the worst. The impact of hyperparameter choice across all models is higher than on FB15K237. There is higher variance. Loss function was always cross-entropy, in line with the previous study. It was by far the hyperparameter with the biggest impact. For RESTcore and TransZ, the next best configuration that did not use CE had a performance drop of 9%. For Dismalt and Complex, the performance drop was about 4.5%. Training type was 1 versus 0 for all models except TransZ, where the only possible training type was negative sampling, and it had an impact of approximately 1% for all models towards the next best configuration. As you can see in the box plot, the brown bar, which is 1 versus 0 plus cross entropy, typically had the highest median validation MRR. During this project, I experienced a number of challenges, from the initial Unicode encoding issues, during the AFB RDF parsing, to the CUDA running out of GPU memory, SSH connection drops, much greater computational load than initially planned for, and memory leaks within the initial code. A couple of lessons learned from this experiment is that wrangling data is very important, using automation with the use of bash scripts and in order to reduce downtime at night is very beneficial. Training in the cloud is very expensive. Each Google Cloud Platform virtual machine with a GPU costs about $1,500 a month, and it is very hard to get GPU quota on Google Cloud project. My request was to get 4 GPUs for my projects. The virtual machines got declined, and I had to work around it with separate billing profiles. Okay, to conclude. Our experimental work, we used experiments to compare the composable KGE models and to search for the best hyperparameter configurations. We used AFB and MUTAG domain-specific datasets. We used the libkge library to ensure a fair and reproducible search. It compares with similar experiments on other datasets such as FB15K237 and WNRR. We used MRR and HITSA10 to compare the models. And for our results, to conclude, Dismalt outperformed the other models on both AFB and MUTAG. Choice of loss function was by far the highest impact on performance, followed by the training strategy. The best models had the 1 versus 0 training strategy and cross-entropy loss function, except TransZ, which used negative sampling and cross-entropy. Overall, all models performed better on domain-specific datasets compared to generic one in previous studies with the same setup, and we concluded that the ontological structure and intrinsic redundancy in expressing facts and domain-specific datasets contributes to better KGE performance. Thank you for your attention. Feel free to reach out if you want to discuss further.